Yes. All right, well, welcome back. We're a little bit behind time, but I figured we wanted some time for some snacks and coffee before getting into this session. So welcome to the 5th session of this symposium. It's Dynamics with Ultrashort Pulses and Ultracold Atoms. We have two very interesting talks coming up, one from Brett Esri and the other from Thomas Pohl, on very different subjects, kind of the same subject from two different angles, I think, in some way. Right, so just to give you a little bit of background about me, I'm Seth Rittenhouse. I was a ITAMP fellow here from 2009 to 2012, so fairly recently. I think I'm the youngest one that's been in front of you so far. Just what I did while I was at ITAMP on a few different areas. I worked on low-energy few-body dynamics, a lot of Efimov physics, and three-body or few-body inelastic scattering processes. Also did some Rydberg molecule things, these trilobite states and large permanent dipole moment systems and polyatomic work. And then I also dabbled in some dipolar molecular BEC while I was here. But you'll notice in this list of things, and actually I should point out I wanted to put up, I've seen some of the other discussion leaders put up a list of the people at ITAMP that I got to work with, either through the visitors program or other postdocs or fellows. And I realized I ran out of space on the slide because I got the opportunity to work with so many amazing people here, so I just left them all out because, it's my work. But you'll also notice that in this list of things, there's not a single statement of intense field or polaritons. So I was a little bit at a loss when I was trying to think about how to introduce this. So I emailed Brett to ask him a little bit about what he was going to talk about, and he was kind enough to give me some kind of general articles that I could read from. So I kind of came up with my own interpretation of what this session is about. It's nonlinear optics, which is basically what everything in optics is nowadays, right? But the basic concept, I thought, was this idea of a strong light-matter interaction. And these two talks come at it from two very different directions. One of them, kind of a more traditional direction of just putting really, really high fields into some matter, like some noble gas or something like this, and seeing some very strong nonlinear effects coming out. The other direction that Thomas will be talking about is sort of tuning or using strongly interacting matter to adjust or to create these nonlinear kind of light matter systems. So to give my interpretation that I learned from Brett in the papers he sent, just to give a little bit of a background on the high harmonic generation side of things, here's a figure I stole from this Nature Physics kind of progress report in 2007 from Paul Corkum and Krauss. And it's a picture of the pulse duration of lasers as a function of years. And you can see that starting in 1964, some time ago, this idea of mode-locked lasers and the frequency comb came about. We started getting this steep decline in the pulse duration of ultra-fast lasers. But then around 1984 or so, that kind of flattens out. You can say that, I'll even say it there, right? At about the 6 femtosecond level, which I already think is really quite amazing. I mean, that's like 3 oscillations of the laser field within one pulse. That's on its own pretty impressive. But it's sort of as far as could be achieved at that time. And it stayed that way for 15 years or so. But then 2011 came about, and as the first sub-femtosecond, the attosecond kind of time scales started appearing. Right? And so what was the reason for these sort of ultra-fast, ultra-fast, we'll say, pulses? Where did they come from? It came from like a completely new mechanism, this idea of high harmonic generation. So here's my intensity or high intensities creating nonlinear response from a simple few-body physicist point of view. Right? I am but simple few-body theorist from Forest of Washington. So this is my idea. It's, put on a strong enough field to a system, and it'll absorb a whole bunch of photons, and only one will leave. I'm calling this the photon thunderdome. Right? Many enter, only one leaves. Bigger, better, stronger. So this is kind of my picture, but what is the mechanism for it? And this is why it was good to have the Corkum papers because there's this model developed by Corkum that is the three-step model. These incredible intensities inside these ultra-short pulses can be used now to create this high harmonic. And the way it happens is this very strong field hits a whatever molecule, atom, whatever thing you happen to have sitting in there. And that really strong field lowers a tunneling barrier for an electron inside that system. Right? That lowered tunneling barrier allows the electron to tunnel out. Right? Then you can use this semi-classical kind of picture of propagation. The electron then can get sloshed over by this strong field, and then when this field flips back over, it sloshes back at it, picking up a whole bunch of kinetic energy. And the electron then can recollide with its parent ion, whatever's left over, and recombine with it. And in that recombination releases all that kinetic energy it picked up in this sloshing mode, or this sloshing, as a high energy photon. Very, very high frequency photon. In fact, in the ultraviolet or soft X-ray frequencies. So this is my picture of high harmonic generation, which is the first thing. So this is kind of a traditional, well, maybe not traditional, but a idea of how really strong fields can create nonlinear response in a medium. The other direction we can talk about is by engineering interactions in a system to create nonlinear behaviors. Right? In this case, you can talk about Rydberg atoms. You can make Rydberg atoms that interact very, very strongly. Right? So you excite to a Rydberg state, or two Rydberg states between two atoms, and you get this van der Waals interaction, 1 over r to the 6. And in my world of ultra-cold physics, 1 over r to the 6 is short range. That's a zero range interaction. That's all we care about. But when you're talking about Rydbergs, you always have to remember that Rydbergs are big floppy things, and they respond really strongly to everything. So this 1 over r to the 6, this C6 coefficient, actually ends up scaling like the Rydberg excitation to the 11th. So you can get these incredibly strong interactions between Rydberg atoms. Right? So those incredibly strong interactions then do an interesting behavior, and that's just my quick version of the idea of the Rydberg blockade. If you want to have two Rydberg excitations nearby each other, right, what happens is this strong interaction shifts the excitation energy of the second one, just because it's so strong. So at some point, that shift is going to be so great that you're well outside of the Rabi frequency of your laser excitation, and you can no longer excite. So at some point, you'll get to a density where you can only get one photon in at a time. Even if you try and shoot two in, you can only absorb one at a time. Right? So this engineering of strong interactions through the Rydberg system then can give us this nonlinear light-matter interaction. So that is the entirety of my introduction there. So with that, I just want to introduce Brett. So Brett was a fellow here from 1997 or 97 to 99. Is that right? He came here from Chris Green's group in Gila, where he graduated 97, and I believe, yeah, you were the first theorist to win the Demob Thesis Prize, I believe. Maybe. I think so, yes. Right, not the, woo!
Of course, right? I tied with an experimentalist, so I couldn't go all the way.
Yeah, since I think there's only one theorist that's ever won it solo, and that's Anna Maria, who wasn't able to be here with us. Right. So, but then after ITAMP, he went to K-State, where he took a position and has been ever since. Basically, Brett has had his hand in all areas of AMO physics, but this is the little-known area that gets ignored here at ITAMP occasionally, as I've heard. So with that, I'll turn it over to Brett.
Thank you. So, take the opportunity today. I have a